Welcome to Tomorrow Unveiled. If you're following AI, you know the paces. Well, it's intense.
It really is. It feels like things are accelerating almost week by week.
Exactly. And it's starting to reshape things in fundamental ways, isn't it?
Yeah.
How we work, how systems operate.
Absolutely.
So this week on Tomorrow Unveiled, we want to cut through some of that noise. We'll look at the really significant breakthroughs, the big shifts that our research team has been tracking.
Yeah. The goal is for you to walk away with a clearer picture of where things are really heading. Not just the splashy headlines, but the underlying currents.
Okay, so what's the big theme you're seeing from this past week?
I think the major signal is this profound shift. A move away from static, pre-trained AI.
You mean models that are trained once and then that's it?
Precisely. We're moving towards systems that are dynamic, that can continuously learn, and also a shift from individual tools like a single chatbot to these interconnected, almost autonomous agent systems. And underpinning some of this, new hardware foundations are emerging beyond just traditional computing. It feels like a move from what's possible, in theory, to what's actually getting deployed, or close to it.
Right, the deployable phase. Let's start with that dynamic intelligence idea. Self-adapting AI. I saw mentions of something called the SEAL framework.
Yes, SEAL. It's a really good example of this trend. Our dedicated research team highlighted this one. The core idea is that these AI models can autonomously improve themselves.
How? By generating their own training data.
Exactly, and their own optimization instructions. So unlike current models where the knowledge is essentially frozen after training,
Right, like a snapshot in
Yeah.
time.
SEAL uses the model's own ability to generate text and ideas to create what they call self-edits. It literally updates its own internal workings based on new information.
Wow.
And it does this using a reinforcement learning loop. So it tries something, sees if it works, learns, adjusts. It's a fundamental break from that old train then deploy model.
So it's like continuous autonomous improvement. The AI is constantly learning on the job, so to speak.
That's a good way to put it. Constantly grading its own homework and figuring out how to get better.
The potential there seems huge. I mean, think about fields that change incredibly fast, like legal regulations or medical research.
Absolutely. An AI using this kind of approach could potentially maintain deep expertise, updating its knowledge far faster than human teams could manage.
But there's always a but, isn't there?
Yeah,
I've heard concerns about something called catastrophic forgetting. Sounds pretty dramatic.
it is a significant challenge, yeah. The research team flagged this as critical. Catastrophic forgetting is basically the risk that as the model self-edits and learns new things,
It might overwrite or degrade the old knowledge.
precisely, it could lose previously acquired skills or information. So ensuring stability and predictability, making sure it doesn't suddenly forget everything it knew yesterday, is a major hurdle researchers are actively working on.
Okay, that makes sense. So if we have these potentially smarter, self-adapting models, how do we actually use them effectively across, say, a whole business? That leads us to the next big shift, right?
It does. It leads right into the idea of industrializing AI and the rise of what people are calling agentic systems.
Agentic systems.
Mm.
So moving beyond just having a helpful chatbot or a co-pilot writing code.
Exactly. The focus is shifting towards orchestrating whole teams, really, of AI agents. Right.
Oh.
Second, distributed intelligence breaking down complex tasks so specialized agents can handle different parts. Third is layered decoupling, basically separating different functions like the core logic, the memory, the tools.
Makes sense. Keeps things organized.
Fourth, vendor neutrality, avoiding being locked into a single company's ecosystem. And finally, and this is crucial, governed autonomy.
Governed autonomy. So they're autonomous, but with rules.
Exactly. Proactively controlling their behavior, setting boundaries, ensuring they work towards the intended goals safely. It's a framework for building these complex systems in a manageable way.
Are we seeing this actually happen yet? Or is it still mostly theoretical?
We're starting to see real-world manifestations. Take Amazon's recent announcement, for example. They talked about AI impacting corporate roles, suggesting a move towards using internal AI services to innovate, maybe even replacing some traditional team structures. That signals a strategic shift. And in specific sectors like retail banking, the research highlights examples where AI agent systems are handling entire workflows like credit risk assessment, speeding things up, boosting productivity, or
Wow.
think about market research. Agents autonomously monitoring data streams, spotting anomalies, generating reports, saving huge amounts of time and resources.
That sounds incredibly powerful. Almost. Too good to be true. What are the pushbacks or the challenges people are raising about this agentic AI mesh idea?
Yeah, there's definitely a debate emerging. While the vision is compelling, many practitioners, the people actually trying to build these things, are raising red flags.
Like what?
While they warn about potentially fragile systems, the coordination complexity getting all these autonomous agents to work together smoothly can just explode exponentially.
Right, like herding cats, but the cats are super intelligent and can access the internet.
Sort of. You can get failures in context sharing, where one agent doesn't fully grasp what another is doing or why, and the costs, both computational and financial, could become prohibitive.
So there's a gap between the grand vision and the current engineering reality.
A significant one. It highlights that the path forward is still very much under construction. We know the destination, maybe, but figuring out how to build the roads is the tricky part.
Okay, shifting gears a bit. Let's talk hardware. We hear a lot about AI needing more and more computing power. And now quantum computing is entering the conversation more seriously.
Yes, the quantum AI convergence. This is really exciting. Quantum computers, as you know, operate on fundamentally different principles.
Using quantum mechanics, qubits, superposition,
Uh-huh.
all that mind-bending stuff.
Exactly. And they hold the potential to solve certain problems that are just completely intractable for classical computers, even supercomputers, especially problems relevant to AI.
How so? What can quantum do for AI specifically?
Two main things, potentially. Dramatically accelerating the training process for certain types of complex models and solving extremely complex optimization problems, finding the best solution out of a vast number of possibilities.
Okay, and there's been a specific breakthrough recently, something called zero-level distillation.
Yes, this is quite significant based on the research we reviewed. It's a new technique for quantum error correction. Essentially, it drastically reduces the resources needed to create something called magic states.
Magic states. Okay, you have to explain that one. Sounds fantastical.
Ha, it does. But they're very real and very important. Think of magic states as highly specific, very pure quantum states that are necessary to perform certain crucial operations for universal fault-tolerant quantum computing. They're like a key ingredient, but they've been notoriously difficult and resource-intensive to create reliably.
So they're essential, but hard to make.
Exactly. This zero-level distillation method provides a much, much more efficient way to produce them. Exponentially more efficient, in fact.
And the implication of that is?
It significantly shortens the timeline for building practical, fault-tolerant quantum computers. It tackles one of the biggest roadblocks.
Wow, so applications that seemed maybe decades away?
Hmm.
Like simulating molecules perfectly for drug discovery?
Precisely. Or running incredibly complex financial models like Monte Carlo simulations with unprecedented speed and accuracy, even potentially breaking current encryption standards, which has huge security implications.
So practical quantum computing gets closer, and that directly fuels the next wave of AI capabilities.
That's the connection. It opens up possibilities for AI that we just couldn't contemplate with classical hardware alone.
Okay, so we have AI getting potentially smarter and more autonomous, and the hardware getting fundamentally more powerful. Let's look inside the models themselves, how AI thinks. There's this interesting phenomenon called the lost-in-the-middle problem with LLMs.
Ah, yes, positional bias. It's a well-known issue.
Can you explain it? I think many people might have intuitively noticed it.
Sure. It's where large language models tend to be pretty good at recalling information presented at the very beginning or the very end of a long piece of text you give them.
But they struggle with the details buried somewhere in the middle.
Exactly. It's like reading a long report. You remember the introduction and the conclusion clearly, but the specifics in Chapter 5 get a bit hazy. For a long time, we just observed this happens with LLMs.
But now the research team indicates we know why it happens, the mechanics behind it.
Yes, that's the recent development. Researchers have pinpointed specific architectural reasons. One is causal masking. The way the model processes information sequentially inherently gives more weight to what comes first.
Okay.
And the second is layer amplification. This initial bias towards the beginning gets magnified as the information passes through the multiple layers of the neural network, so the problem gets compounded.
Understanding the why is huge, right?
Right.
Because it means we can start engineering solutions.
Precisely. It transforms it from just a weird quirk into an engineering problem you can tackle. You can explore alternative masking techniques or maybe adjust the network architecture, the number of layers, to get more consistent performance.
Which is critical if you want to rely on these models for things like legal document analysis or summarizing medical records, where missing a detail in the middle could be disastrous.
Absolutely. It's key for building more trustworthy and reliable AI.
And there was another interesting finding related to how AI might be thinking, wasn't there? Something about conceptual categories.
Yes, a fascinating side note from the research. Some studies are showing that certain LLMs, when asked to sort objects or concepts, spontaneously form categories that are surprisingly similar to human conceptual categories.
So not just pattern matching, but something more like understanding.
It suggests they might be developing internal representations of objects and concepts that are more analogous to how human brains organize information than we previously thought. It's early days, but it's a really intriguing hint about their internal workings.
Okay, this ties back nicely to the hardware point. If models are getting more complex, maybe even thinking in more complex ways, the hardware needs to keep up. We talked quantum, but what about more near-term advances beyond standard GPUs?
Right. GPUs have been the workhorse, but AI's appetite for compute is insatiable. So, new hardware paradigms are emerging fast. Neuromorphic computing is a big one.
Brain-inspired computing.
Exactly, mimicking the structure and efficiency of the human brain. Our research team highlighted Sandia National Laboratories deploying a system called Spinnaker 2.
And the scale is impressive.
It simulates around 175 million neurons. But the key isn't just scale, it's efficiency. For certain types of AI tasks, especially parallel processing like in sensor networks, it can be drastically more energy efficient than GPUs.
How much more efficient?
The figures suggest up to 18 times more efficient for some specific workloads. That's huge, especially for AI deployed on edge devices like phones or sensors where power is limited.
And are there other approaches besides neuromorphic?
Yes, definitely. There's a lot of progress in analog AI chips and in-memory accelerators. These perform calculations directly within the memory chips themselves rather than constantly moving data back and forth between memory and processor like traditional systems.
Cutting out the data transfer bottleneck.
Exactly, which promises significant improvements in performance per watt, getting more computation done for the same amount of energy.
So these aren't just lab experiments anymore.
They're moving into real-world applications. We're seeing them integrated into cloud platforms, specialized AI accelerators. This new hardware is getting ready to power the next wave of AI, embedding these advances into everything.
It's an incredible convergence of software, algorithmic understanding, and now hardware innovation. But with all this power and increasing autonomy, we have to talk about the risks, the challenges.
Absolutely critical. The perils of autonomy are very real. We mentioned catastrophic forgetting and instability.
Right, model degrading.
But there's also the challenge of goal misalignment and emergent behavior. What happens when an AI agent figures out a shortcut to achieve its goal, but it's not the way we intended? Maybe an undesirable way.
Like the examples researchers found of AI learning to cheat in games to win.
Exactly. Or AI drift, where the AI's behavior slowly changes over time, diverging from its original programming in unpredictable ways. And then there's security.
A whole new attack surface.
A huge one. Autonomous agents that can use tools, access data, they become targets for things like prompt injection, tricking the AI into doing harmful things, or tool misuse. And, of course, the potential for malicious actors to deliberately weaponize these agentic systems.
It's a complex threat landscape.
It really is.
And that brings us to the ethical guardrails, the safety considerations. As these systems become more autonomous, more self-modifying, the lines blur, don't they?
They really do. Accountability is a massive question. If an autonomous AI agent causes harm, who is responsible? The developer, the user, the AI itself. It's a huge legal and ethical gray area we're only beginning to navigate.
And the risk of bias.
If a system is continuously learning and adapting on its own, it could potentially amplify existing societal biases present in its data at an unprecedented scale without direct human oversight to catch it.
The black box problem also gets worse, presumably. If the AI is changing itself, how do we understand why it makes a certain decision?
Exactly. Transparency and explainability become even harder, which undermines trust and makes it incredibly difficult to debug when things go wrong.
And data privacy must be a major concern, too, with agents potentially accessing vast amounts of information.
A huge risk. Compromised or even just poorly designed agents could lead to significant data leaks of sensitive personal or corporate information. These aren't future problems. They are here and now challenges that need careful consideration alongside the development.
Definitely a lot to think about there. Just a quick reminder for everyone listening, if you find this insightful on YouTube, please do take a second to like the video, subscribe to Tomorrow Unveiled, and hit that notification bell so you don't miss our future updates.
And if you happen to be listening on a platform like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It genuinely helps new listeners discover the show.
So, pulling all these threads together, what's the big picture looking forward? These trends, dynamic intelligence, agentic systems, new hardware, they seem deeply interconnected.
They absolutely are. What this week's research really highlights are these three dominant converging trajectories. One, the shift from static AI to dynamic, learning AI. Two, the industrialization of AI through agentic systems aiming to transform core business processes. And three, the emergence of quantum and novel hardware as new foundations, unlocking new capabilities.
Okay, so what should we expect in the, say, near term, the next 1 to 3 years?
I think we'll see intense focus on tackling those challenges we just discussed: stability, control, safety for these self-modifying and agentic systems. Lots of research there. We'll also see enterprises refining their AI architectures as they gain practical experience, moving beyond the hype to what actually works.
And hopefully better LLMs that don't lose things in the middle.
Yes, expect a new generation of models that specifically address that lost in the middle problem, making them more reliable for those critical tasks. The path to deployment will get clearer, probably a bit messier than the initial grand visions, but
Yeah.
clearer.
And longer term, 5, 10 years out,
Mm.
what's the potential vision then?
Looking further out, you can envision really advanced systems. Think specialized, self-improving AI agents collaborating, running on maybe hybrid classical quantum hardware stacks, solving problems we currently consider intractable in material science, personalized medicine, complex system modeling.
But the challenges scale up too.
Profoundly, the questions of control, safety, ethics, and governance will become even more central, more urgent. It's not just about technical capability anymore. It's about managing that capability wisely.
So the discoveries this week, they're not just new tech. Thank you so much for joining us on Tomorrow Unveiled. We'll be back next time to continue unpacking the future together.